In this question, we're told we have a cube of density 2,490 kilograms per meters cubed. It's suspended from a force meter in a giant beaker of water so that it is fully submerged as shown in the diagram. So we've got our cube here. It's hanging from our force meter, which is out of the water, and the cube is totally submerged in the water. It's underneath the surface. Okay, so our eventual goal is going to be figuring out the apparent weight of the cube as measured by the force meter. So to figure out whatever value our force meter will be reading. Okay, so let's go through the steps we've been given here. First, we're going to figure out the volume of the cube. The volume of a cube is given by the length of the side to the power of 3, or cubed. And we can see from the diagram provided that one side of the cube has a length of 0.10 meters. So we're going to be doing 0.10 meters cubed, and that's going to get us a volume of 0.001 meters cubed. Next, we're going to use that volume to figure out the buoyant force acting on the cube. Let's head to our reference sheet. Here's our equation for buoyant force. The buoyant force is equal to the density times g, which is 10, times the volume. Now be careful, because the density is the density of the fluid that the object is in. It's not the density of the object. V is the submerged volume of the object. So we just have to be really careful when we're putting in our numbers into this equation. So our buoyancy force is the density of the liquid multiplied by G multiplied by the volume of the object. Okay, so we can go ahead and put in our numbers. The density of our liquid, well, the liquid is water. We know that water has a density of 1,000 kilograms per meters cubed, multiplied by G, which is 10 on Earth, multiplied by the volume of the object, which we just calculated. It was 0.001 meters cubed. So putting that all into our calculator gets us out a buoyant force of 10 newtons. So we can see here, for a buoyant force, the things that affect it are the density of the liquid, here that's water, G, which is always 10 on the surface of Earth, and the volume of the object. So the bigger an object is, the more volume it has, the more water it displaces, that increases the buoyancy force. Or the density of the liquid that it's in, that increases the buoyancy force. But the density of the object itself doesn't affect the buoyancy force. Our cube, we're told, has a density of 2,490 kilograms per meters cubed. That doesn't impact our buoyancy force at all. The only things that matter are the density of the liquid and the volume of our object, along with G. All right, okay, we've got our buoyant force. Next step, we want to figure out the weight of our cube. So first we want to figure out the mass of our cube. We know its volume from this first question. We know its density, so we can use the density equation to figure out the mass. Here's our definition of density equation. Density is mass divided by volume. So density is mass divided by volume. We're trying to find the mass, so I'm going to multiply by volume on both sides so that will cancel on the right. So our mass is our volume times our density. Remember, now we're talking about the cube, so that's the density of the cube and the volume of the cube. So our volume of our cube we already calculated in the first question. It's 0.001 multiplied by the density of the cube, which we're given in the question is 2,490 kilograms per meter cubed. That gets us a mass of 2.49 kilograms. So we can go ahead and fill that in here. 2.49 kilograms. That's our mass of our cube. Next, to find the weight force, we're going to be using our weight equation. W equals m times g. M is the mass. We just calculated that. It's 2.49 kilograms. Multiplied by G, the gravitational field strength on Earth, which is 10. That gets us a weight of 24.9 newtons. So let's go ahead and fill that in here. Wonderful. Okay, so we've figured out the buoyant force acting on the cube. We've figured out the weight force acting on the cube. So let's go ahead and draw ourselves a free body diagram at this point. So if this is our cube, we know we have a weight force acting downwards. We know we have a buoyant force, I'm going to label it B, acting upwards. And we also have the force meter, which has a string attached that's pulling up on our cube as well. I'm going to call that our tension force. The tension is the force pulling up on our cube from our force meter. So those are our three forces acting on our cube. So I can fill in that next question. How many forces are acting on the cube? We've got 3. Our next question asks us for the magnitude of the net force acting on the cube. Now we know from Newton's second law that the net force is equal to the mass times the acceleration. If our object is accelerating, we've got a net force. If our object is not accelerating, then our net force will be 0. Now in this question, our cube is just suspended in the water. It's not moving at all, it's stationary. So our acceleration in this question is going to be 0. That means that our net force must also be 0 because we're not moving anywhere. So we've got a net force of 0 newtons. Now our final goal is to find T. That's our apparent weight of the cube measured by the force meter. So I'm going to figure out an expression for the net force acting on our cube. And I know that that's going to equal 0 because I know my cube isn't accelerating. So in the upwards direction, I've got the buoyant force and I've got the tension. In the downwards direction, I've got the weight, so I'm going to subtract that. And I know that that net force is equal to 0 because my object isn't accelerating. I want to find T. So I'm going to add weight on both sides to start with. So that will cancel out on the left. So now I've got B plus T is equal to W. And I'm going to subtract B on both sides so that that can cancel on the left as well. I'm left with T is equal to W minus B. So let's put in our numbers now. W, the weight, was 24.9 newtons. I'm subtracting B, the buoyant force, which we calculated as 10 newtons. That gives me a T, a tension force of 14.9 newtons. Now remember, that is the force pulling up from our force meter. So that's the force that's going to be measured by our force meter, or in other words, the apparent weight of the cube, which is 14.9 newtons. So we can go ahead and fill that in here, 14.9 newtons. So in this question, you can see we're using a typical force diagram or free body diagram. We're using Newton's second law to figure out what's going on. The special things we have to do are figuring out our buoyant force using the buoyant force equation. Remember, the density is the density of the liquid, not the object, and the volume is the volume of the object, not the liquid, in our buoyancy force equation. We're also calculating the weight using W equals mg and putting them into our expression for net force. In this case, our object wasn't moving at all, so the acceleration was 0, and our net force was 0. In this question, we have a cube of unknown density floating, partially submerged in a giant beaker of water, as shown in the diagram. So we can see here, this part of our cube is underwater, and this part is above the waterline. We're also told the cube has a side length of 0.28 meters. So we can draw that on the diagram. The length of one of the sides is 0.28 meters. Okay. So we're going to start out by figuring the volume of our cube. Remember, the volume of a cube is just the length to the power of 3, or cubed. Our length was 0.28 meters. So that's cubed. That gives us a volume of 0.022 meters cubed. So we can go ahead and fill that in first. 0.022 meters cubed. Great. We've got the volume of our cube. Now we're trying to figure out the buoyant force acting on the cube. Let's go ahead and find our equation for that. Same as before, here's our equation. Buoyant force is the density of the fluid times G times the volume of the object. So our buoyant force is the density of the fluid times G times the volume of the object submerged in the water. So in order to find the buoyant force, we need the volume of the cube that's submerged. But remember, in this question, the whole cube isn't submerged. Only this part is submerged. We can see by the markings on the cube here that we have 2/3 of our cube submerged in water and 1/3 of our cube is above the water. So if we know we have a total volume of 0.022 meters cubed and 2/3 of that is submerged in the liquid, then our volume submerged is going to be the total volume, which is 0.022 multiplied by 2/3. So 2/3 of that is underneath the water. That gets us a submerged volume of 0.0146 meters cubed. Let's fill that in to check that was correct. Awesome, okay, so we've got the volume of the cube submerged in the liquid. Now we need to find the buoyant force acting on the cube. Again, we're using this equation. Remember that the density is a density of the liquid, not the density of the object itself. We're in water. We know the density of water is 1,000 kilograms per meters cubed, multiplied by G, which is 10 on Earth, multiplied by the volume of the object submerged in the water, which was that second volume we just calculated. It's 0.0146 meters cubed. That gets us a buoyancy force of 146 newtons. Let's go ahead and fill that in here. Okay, so we figured out our buoyancy force. Now let's go ahead and draw a free body diagram. So here's our cube. We know we have a buoyancy force pushing upwards on our cube because it's partially submerged in water. We also know our cube has a weight because it has a mass. So we've got weight force pushing down. And in this question, that's it. We don't have any other strings attached to our cube causing any tension. We've just got two forces. So we can fill in our next question. There are two forces acting on the cube. In this question, our cube is floating, which means it's at equilibrium. It's just sitting there. It's not moving or accelerating. Therefore, we know our net force must be 0 acting on the cube. And we can now use our net force and the fact that it's going to equal 0 to figure out our unknown weight force. So our net force is going to be our force upwards, which is buoyancy force, minus our force downwards, which is weight. And we know that's got to be equal to 0 because our cube isn't accelerating. So all we need to do is go ahead and add weight on both sides. It's going to cancel on the left. And we know that our buoyancy force is equal to our weight. So since our buoyancy force was 146 newtons, our weight must also be 146 newtons. So let's go ahead and fill that in here. We know our weight force must be equal to our buoyancy force, so it's 146 newtons. Awesome. Now we can work backwards to figure out the mass and density of our cube. We know the weight, and we know we have the W equals mg equation. We're trying to find the mass. Right now, mass is multiplied by g in the equation. So I'm going to divide by g on both sides. The g's cancel on the right, leaving me with mass is equal to weight divided by g. So I can go ahead and put in my weight force, which I know is 146, divided by g, which is 10 on Earth. That gets me 14.6 kilograms for my mass. Finally, I can find the density of the cube. Our density equation tells us density is mass divided by volume. Density is mass divided by volume. We're trying to find density, so this is already arranged correctly for us. We just put in our numbers. Our mass we calculated as 14.6 kilograms, divided by our volume, which we calculated right at the top. It's the volume of the whole cube now, not just the volume submerged. The volume of the whole cube was 0.022 meters cubed. Putting that into our calculator, that gets us a density of 667 kilograms per meters cubed. So let's go ahead again and fill that in to make sure that's correct. Awesome. Okay, so again, you can see in this question, it works just like any other problem with a force diagram. In this question, we had buoyancy force upwards. The buoyancy force is calculated from the density of the liquid, not the density of the object, and the volume of the object that is submerged in the liquid. So here it wasn't the whole volume of the cube, it was 2/3 of that volume because we only had 2/3 of the cube under the water. Then our weight force had to be equal to that because our cube was stationary in the water. So we knew those balanced each other out, and we could work backwards from the weight to find the mass and then the density.